Okay, previously we talked about the Nyquist stability theorem. Okay, and then I have a trouble in the third and fourth part. Okay, if you remember. But nonetheless, you just memorize the definitions. So now we go to gain and phase margin. Okay, as previous videos we also talk about it. I mean the introduction. We discussed that the phase margin is actually your distance from the amount of distance from some point to the limit. Okay, so in other words, maybe I should show you. So if you're here, okay, let's say if your system, your Nyquist plot is about here, right? The amount of distance from your point to the limit minus 1 is some values, right? This is actually lambda. Okay, this is actually the margin. This is called the margin. Okay, so the larger you are, the whole one. I say that this is margin. Okay, this is actually wrong. Okay, this is not. Okay, sorry. Yeah. So my understanding is not strong enough. Okay, so this is actually the I call it lambda. I don't call it a margin. Okay, gain margin is simply okay. Um, this lum this this distance, okay, from the origin divided by where you are. Okay, it will give you a distance of, it will give you a magnitude of how much. That means you're comparing your this one to this one by how many times, right? So it give you a multiplication of a factor. Let's say if you are, let's say this is 100, right? So if you're at 10, okay, 100 divided by 10 is equals to 10. So you are 10 times further away from the limits. This is what it means. Okay. So if let's say you are at 20 now, okay, you are actually 5 times away, right? If you are 90 now, okay, so 100 divided by 90 is equals to, what do we have? You're actually 1.11 times near, so you're going near to there. So you're reaching, so you're from some values, big values, okay, big values, you're reaching towards the limit, the value of the limit. So if you're 100 over 100, you're actually equals to 1, right? So if you are larger than 100, let's say you're 200 now, you're actually further away from the limits already. So the gain margin is simply, okay, I say so much. The gain margin is simply 1 over lambda. Okay, it's a scaling factor. This one is the radius 1, right? Okay, so any radius 1, okay, anywhere over here, okay, is considered this thing. Okay, this is the limits. So the limits divided by where you are, okay, will give you how much, how many more times can you allow to reach a certain point. Okay, so in the previous video, I said about the margin. Yeah, it is not that correct. Okay, it's not that correct. Although the concept shares the same point, but it's not that correct. So if you were to come back here, this is what I'm talking about, the gain margin. So it's defined as that factor by which you would have to increase the gain to get instability. Okay, it's in terms of the factor. Okay, so how many times you compare the limit to the distance from the origin, right? So I hope I give you a very clear understanding of what actually it is. And then it is calculated by determining the magnitude, this lambda, okay? And then when the transfer function is equals to negative 180 degrees, okay? So the transfer function is minus 180 degrees, which is this one, right? So it is actually, if you remember last video, okay, we talked about the So as you can see, the gain is equals to 1. Okay, the gain is a magnitude of 1. Okay, it can be -1, it can be 1, but if you magnitude, okay, if you modulus them, they are all equals to 1, right? So this is the gain, and then the phase is actually negative 180 degrees because you're 180 degrees out of phase. Okay, so therefore this will show you that you're actually out of phase. Okay, so this is why this is the somewhat the instability zone, let's say, right? But nonetheless, we just keep it first. Okay, so now we talk about the phase margin. So phase margin is actually equals to the extra phase lag. It's the same thing. Okay, 180 plus your phi is equals to 180 plus this data. So if you were to bring it out, it's actually phi minus 180 degrees. Okay, my fault. Okay, I explain it quite in a bad way. So it will be theta. Okay, so this phi angle, it tells you how much more you reach negative 180 degrees. Okay, this is negative 180 degrees, right? How much more before you reach 180 degrees? This is what it means. Because this is 180 degrees, right? So 180 degrees minus away whatever angle you are. So this maybe I should label in like some green color. So this thing, okay, I hope I draw it clearly. So this thing is actually theta. This is the phi angle. So the theta is your transfer function's lag. Okay, it's a transfer function phase angle. It's a transfer function system. Let's say your input is like that, and then your transfer function it's about starting from here, right? And then in order for the system to be very unstable, your phase angle, so it may be something like that, and then you go unstable, right? So the distance from this point to this point is actually phi, right? So how much more can you allow so to speak that it actually reaches instability, right? So because if you reach negative 180 degrees out of phase, the whole system will go unstable. I cannot prove to you in MATLAB, but this is just the meaning, although the meaning might not be that correct. But this is the thing that I believe so. So this is actually phase and gain margin, and therefore if you take a look in this picture over here, right, this is actually a more nicer drawn picture that I've drawn earlier. Okay, it's the same thing. Okay, it is a real axis over here, and this is the imaginary axis. As you can see, this is the lambda that I'm talking about. Okay, so the magnitude of 1 divided by this position will give you the gain margin. Okay, how much you move, how much more times to instability. Okay, this is something like that. So let's say 110. So you are 10 times more to instability. So you are right safe. So in other words, 1 over lambda, the higher 1 over lambda is, the more stable you are. Okay, so this is the important key point. So if your lambda is smaller, okay, as you can see, if your lambda is over here, right, your factor will be much higher, right? So the higher you are, the more stable you are. This is the key thing I want to convey over here. And then the second one, okay, the second one is actually the unit circle. Okay, I mean the phase angle. Sorry, what am I talking? So the phase angle is actually this one, and this is the theta, right? So this whole so as you remember still, this is the minus 180 degrees, right? So your phase angle, okay, because minus 180 or 180 degrees is always is whatever the case, because you're talking about the whole radius 1. Who cares minus 180 degrees or 180 degrees? If you're over here, if you reach here, you're dead lah. That's what it means. Okay, if you so yeah, so simply this is the same thing as the gain margin understanding. Okay, so the phase margin is actually how much more um before you reach instability. Okay, which is over here, right? How much more before you come here? Okay, if let's say you have maybe this is 10 degrees, so you're 10 degrees more, you're 10 degrees more to instability. Okay, if you're over here, okay, let's say this is 30 degrees, you're about 150 more degrees. Okay, this is 5 to 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 instability. So in this case, let me ask you a question: is which phi angle will be more stable? Is this phi angle more stable or this phi angle more stable? Actually, in fact, it's this one. This is more stable. Okay, this is more stable because you're further away from the your phi angle is larger. Okay, so from here you can conclude gain margin higher better. Phase margin higher better. Okay, so you need to remember that. So higher is better. Okay, and then how does the phase margin works? Okay, so let's say you have a root locus. Okay, let me draw it up. Actually, no need to draw lah. Okay, this is the root locus. What the hell am I talking? So this is the root locus. Okay, in from omega is equal to 0 to omega is equal to infinity over here, right? That way there may be a negative frequency. Okay, so this is if you were to see, okay, if you were to go all the way up, okay, so omega is equals to 0, and then all comes all the way to omega is equals to infinity. Eh? Maybe the other way lah. Sorry. Yeah, whatever lah, okay. So we are talking only about omega equals to 0 to omega is equals to infinity, that's all. Okay. And then what do we need? Okay, what we need to know over here is that if your root locus is at this point, you want to know which is the point that you want to look at it, right? Which is the instability point, which is the critical point that you're talking about. We have this point and we have this point. Okay, so you have to compare which frequency. Okay, it's I mean which, because at here the frequency maybe some value is 100 and this is maybe 20. Okay, because you're coming from omega equals to 0 to omega is equals to infinity ma. So as you goes by, this value will become larger. So we have to compare which frequency is actually safer. Okay, so if I were to take this frequency, okay, how much more do I go to instability, or how much lag? Okay, if you choose here, okay, you're actually minus 180 degrees out of phase. Okay, if you take a look, if any one frequency produce 0 dB gain, which is the gain is equals to 1, okay, the radius 1 touches the 1 radius, okay, and it's minus 180 degrees phase, your system goes haywire. So there is two conditions, right? So one condition is that if it touches this place, or if it's negative 180 degrees, okay. So is one gain. There is only two conditions. One gain and 180 degrees, you will be unstable. Okay. So in this case, I didn't touch the negative one, but however I have 180 degrees, so I am safe. Okay. However, from here, okay, this point is also, this is still considered safe. Okay, just about safe. Okay. So this point may not have a gain of 1. Okay. Because maybe I hold. If you were to extend to the trigonometry side, okay, this is actually gain equals to 1, right? And then if you were to draw a line, okay, over here, this is actually some value. Okay, this is actually some value. and this is actually some values over here, right? So maybe we call this A and we call this B. So A square plus B square is equals to 1, right? So if the magnitude of this two will give you a magnitude of 1. So in this case, this length and this length should be as lower as possible. Because if you are lower as possible, you're nearer to the origin, right? You're smaller, right? Your maybe I call it C and D. Okay, so C and D is more stable than A and B, right? And therefore, yeah. So typically you wouldn't want to write in terms of so many things, right? Because since you know that the radius is 1, okay, the only thing that I need to know is actually the phi angle, that's all. The angle will tell us A and B, right? If you have a trigonometry and you know that this is 1, okay, and if let's say this is 30 degrees, what do I have for this one, right? I can actually use this is actually h, right? So I can actually inverse sine 30. Sorry, I should not inverse sine but rather than sine 30. Okay, because sine 30 is equal to O over h. So if I bring the h up, which is actually equals to 1, in this case the hypotenuse is 1, right? So therefore sine 30 is actually 0.5. And then now if I have a cosine 30, okay, now this is adjacent, right? Equals to A over h. Similarly, if I cosine 30, what do I have? I have 0.8. So at this distance, if let's say this phi angle is 30 degrees, and then this dude is 0.86, and this portion over here is 0.5, right? So in case instead of writing out all, like I say, you cannot cross this thing, right? It's pretty tough to assemble, like to find. So what they actually say that so in other words, okay, to summarize a better form, okay, so for gain margin is for, so the 1 over lambda, right, for gain margin, which is this one, okay, only applies for when you are at this line. Okay, when you're at this line, you can use the gain margin rule because you're exactly 180 degrees. Okay, over here. So you can straight away use this rule because it really specifies over here. For phase margin, okay, which is this one, okay, it's for when you are not minus 100, is when you are not along this real axis. You are at the imaginary and the real. Okay, you are in both. So you have some points over here, some points. Okay, I think you get what I mean. So which is not negative 100 degrees. And for both cases, gain and phase margin, okay, if let's say for here, or if a point at here, or if a point at here, okay, along the root locus, okay, so this point you use gain margin, and this point over here you use phase margin, okay. So the higher the gain margin and the phase margin you calculated, the more stable you are, okay, as I show you earlier, right? If 1 over lambda is high, this means that lambda has to be low, right? So the distance from here, so you try to the lesser lambda, so in order to be more stable, you have to minimize lambda, okay? And then in order for the phase angle to be big, okay, this phase angle, this is phase angle. For this phase angle to be big, theta has to be small, right? So this phase angle bigger, better, right? More stable. So this is generally the gain and phase margin that I want to convey. I have rambled too much, okay, but nonetheless, unit circle wise, you have to keep within this range. So I actually drew out a Nyquist plot. As you can see, I have drew out the margin. Okay, is from -1 to 1, right? So as you can see, at this point, these 2 points, okay, closed loop stable, yes, okay, but within this unit circle 1 is stable. Outside of this, you so this portion over here, okay, so yeah, so as you can see, this is the margin that I'm talking about. I mean, not margin, but rather this is the parameter that is considered unstable. Okay, I've repeatedly drawn this a lot of time. I just want to convey it in the manner. So another thing that I will convey in the next video, because before I end the phase of margin, okay, is that the higher the k values, okay, so this is that maybe this is k equals to 1, this is k equals to 2, this is k equals to 3, this is k equals to 4, right? So the higher the k values, the more you are closer to the real axis. Okay, the faster you have. Okay, so next video I'll just prove to you for different root locus. Okay, what will the k, as k varies, what will the graph looks like. So I'll see you in the next video for that trend. Okay.